Hello everyone, today I want to talk about magnetic probes. The title of my report is Development of a Compact Magnetic Probe Array in Sino United Spherical Tokamak. First of all, let me introduce our device to you. Its name is Sinist, and it's a small spherical tokamak. Its major radius is 0.3 meters, and its minor radius is 0.23 meters. The aspect ratio is 1.3. The designed toroid field at the major radius is less than 0.3 Tesla. The plasma current is about 15 kiloamp and the pulse length is about 15 milliseconds. In the right is a bird view of Sinist tokamak. Now let's go to today's topic, magnetic probe. We all know that magnetic diagnostic is basic and vital in tokamak operation and related plasma experiments. From the absolute magnetic field strength measurements, equilibrium of the plasma can be reconstructed. Besides, from the magnetic field fluctuation measurements, instabilities of the plasma can be studied. However, the space in the high field side of the compact spherical tokamak is usually very narrow. For example, in Sinist, the radius for the center column is only 16 millimeters, which makes it difficult to install magnetic probe in the high field site, and no magnetic probe is installed there before. In this report, a compact magnetic probe array is installed there and the newly installed probes show good performance. The absolute magnetic field strength measuring error is around 100%, and the probes have a good response to high frequency magnetic fluctuations. The probes are very thin, and the bottom of the forelegs of the probe are curved surfaces, so that they can closely touch the surface of the center post. The ordered turns of the coils are specifically chosen to have good response to high frequency, while maintaining the ability to measure the absolute magnetic field. The probe array has 16 toroidal direction channels and 16 poroidal direction channels. After that, the probe array is shaded by 0.5 millimeter thick curved molybdenum sheet, and the signals are transmitted out by the flexible printed boards. Finally, before sampled by the data acquisition system, a suitable resistance connected in parallel is used to suppress the resistance peak of the magnetic probe. To calibrate the effective array of magnetic probe, the Helmholtz coil is used to create the standard magnetic field. We sweep the frequency of the stimulation from 10 kHz to 100 kHz to get the effective array under different frequency and finally average them. And the effective array for a poroidal direction are around 214 square of centimeters and 105 square centimeters for a poroidal direction. To calibrate the frequency response of the magnetic probe, the LCR bridge is used to measure the magnitude and angle of the complex impedance. Then we try to fit it as a rational function, such as Z equals N over D. Then we can obtain the transfer function H. Given the single pole circled model shown in last slide, the transfer function H from input to output is always 1 over D. Figure A and Figure B are the fitted and measured magnitude and angle of the complex impedance. Figure C and Figure D are the calculated transfer function. From the calculated results, we can see that the frequency response of the poroidal direction can reach 1.1 MHz and 1.7 MHz for a toroidal direction. To calibrate the installation error, we suppose the vertical field as the standard current source and try to get the difference between measured absolute magnetic field and the calculated magnetic field. However, the pulse length of vertical field is very short, so eddy current must be considered. We use the response function method here to subtract the eddy current response. The key point of this method is to develop a model which includes eddy current, and the transfer function from stimulation to response coil is calculated, and the eddy current response calculated in this method is shown in Figure B. Finally, the installation error for the provided direction are mostly below 100%. This is our experimental results. Combined with the magnetic probe array in the high field side and the magnetic measurements in the low field side, we can get reliable equilibrium results. Here we compare the reconstruction results with the picture taken by high-speed camera. In the beginning phase of the flat top, from Figure D, we can see that the brightness of the whole vacuum chamber is uniform, which means that the plasma almost occupies the whole vacuum chamber, including the high field side and low field side, and this coincides with the equilibrium reconstruction results. In the middle of the flat top, from the fast camera picture E, the brightness in the high field side is lower, and the light is mainly from the low field side, which means that plasma is outboard limiter configuration, and this coincides with the equilibrium reconstruction results too. In the ending part of the flat top, from Figure F, the brightness in the high field side is lower again. The light mainly focuses on the low field side, and the long-mirror probe is sparking, which means the plasma's volume gets smaller again, and the plasma is still outboard limiter configuration, and this coincides with the equilibrium reconstruction results too. We also analyzed the signal of magnetic probe during minor disruption. From Figure A, we can see that the minor disruption happens at 16.9 milliseconds, and a wide bandwidth of the frequency spectrum of magnetic fluctuations is observed during the minor disruption. Evidence shows that the magnetic probe in the high field side has a good response to the high frequency magnetic fluctuations. In the future, we can combine the magnetic measurements in the low field side, then mode structure and more detailed minor disruption physics can be studied. Finally, let's take a short summary. First of all, a new compact magnetic probe array installed on the center post is developed for equilibrium reconstruction and instability study on stainless. And the probe array is thin and designed to touch the center post closely. As for the performance, the installation error is mostly within 100%. Therefore, the probe can give a reliable constraint for equilibrium reconstruction. And as for the frequency response, the response function calibration result shows that frequency can reach 1.1 MHz for a provided direction and 1.7 MHz for a toroidal direction. And the wide bandwidth of frequency spectrum is observed during the minor disruption. And this is my whole presentation. Thank you for listening.